In this final lesson in our introduction to solving differential equations, we're going to look at the connection between differential equations and Taylor series, specifically using a Taylor series to approximate a solution to a differential equation. This is especially useful when for many differential equations where explicit or analytic solutions do not exist or are very, very difficult to compute. Maybe they're differential equations of forms that are not homogeneous or separable or in ways that in the sorts of things we've currently studied. However, we can still come up with very good approximations if we know something about the differential equation itself, and we can find derivatives, or at least the values of subsequent derivatives. Recall that from our study of Taylor polynomials, recall Taylor polynomials have this general form. If we want the Taylor approximation of a polynomial, we need to know the function's value at some initial point, we call that, or the center of the polynomial. Then we took the function's derivative at that center and divided by 1 factorial, which is just 1, times x minus the center. And then we continue building. So the second derivative at that center point over 2 factorial times x minus c squared, and continue. What's nice is that if we're starting with a differential equation, at least a first order differential equation, that we already know, or you can almost always have an initial value for what this first derivative is. That's what dy dx is. So we kind of already have a starting spot here. So if we can find an initial condition, we'll have we can clearly write a first order differential equation. And then if we want to continue and make better approximations, well, we can find subsequent derivatives. Well, how do we find subsequent derivatives? Well, I think f prime, or f double prime, excuse me, that should be the same as just the derivative with respect to x of the first derivative. Or better yet, that would be like the derivative of whatever this function is, whatever this rule for this derivative is, for the first derivative, whatever this rule of, maybe it's got x's and y's in it, and that's fine. We know how to find derivatives of functions with x's and y's already. We can use implicit differentiation to come up with value expressions for what this might be, and we will already know or at least we should already know some values of like what the value of c is, what the initial value, we'll call x naught, and the initial y coordinate as well, x naught and y naught. And so we can plug those in for this formula to come up with a value for f prime or f double prime, and we can substitute that in. If we want a third derivative, we continue the process. If we want f triple prime, if we need to keep going and make finer approximations, we just find the derivative of the expression for the second derivative. And again, substitute in the things we know to come up with a value for what the third derivative of this function should be at that, and continue the process and as long as you need or want. So we've got two examples of both approximating solutions to differential equations, and also these also happen to be differential equations where we actually can find exact solutions, and we can see and we can compare and contrast the difference between the polynomial approximation and the exact analytic closed form of each of these two. So without solving the system, so we're not going to actually separate variables and do anything to try to solve this. We're going to find the first 3 non-zero terms of this Maclaurin polynomial. Again, we call it Maclaurin polynomial, meaning the center. This is the same as Taylor polynomial, but the center is 0. So let's see. What's the first three terms? First three non-zero terms, at least. Well, I know the initial condition. At the center, the output is 1. So we at least have one. We have one non-zero term, and that is the constant term. This is like f of 0. So that's good. Let's see. What's f prime at 0? Well, or better yet, we know what x is at 0. It's 0. We know what y is at 0. It's 1. So dy dx, which is f prime, is at the point 0, 1 is 0 minus 4 times 0 times 1, which is 0. So we're going to get a 0 term here, unfortunately. That's okay. Let's find the second derivative. Let's find f double prime. Well, the second derivative is just the derivative of our rule here. That's just the derivative of x minus 4xy, which is, by my count, derivative of x is 1. Derivative of minus 4xy is minus 4 times product rule. First derivative second, plus second derivative first. I think this should be y plus x dy dx. Again, we're using implicit differentiation. Again, this is a minus 4. We could distribute and combine terms if we need, and maybe we will, and we will in just a moment to find the next derivative, because we need at least one more. But we can find the value of the second derivative at this center point, because we know when x is 0, we know what y is, and we also have calculated what this derivative is as well. We know that the second derivative then is going to be 1 minus 4 times y is, when x at the center of 0, y is 1. So minus 4 times 1 plus, when x is 0, dy dx, we saw the first derivative is also 0. Minus 1 times minus 4 times 1, that's minus 3. Good. So now we have two non-zero terms. We need a third. So let's find the third derivative. That's the derivative of this previous expression. This is not so bad. The derivative of 1 is 0. So what we have is minus 4 times, now let's see the derivative of the inside here. Derivative of y is dy dx, plus derivative of x times dy dx. This is product rule again. That could be, how about derivative of first times the second, which is dy dx, plus this, how about then the first times the derivative of the second? No, it should be x and then the second derivative. Plug in things we know. We know that the first derivative is 0, so this is 0, or maybe we'll combine like terms here just for a future sanity. Negative 4, 2 times dy dx plus x d squared y dx squared. Dy dx is at, when x is 0, dy dx is 0, so this is 0. X, the center point, is 0, so it doesn't really matter with this, even though it's negative 3. Negative 4 times 0, this evaluates out to be 0. So alas, we need to do one more derivative. At least one more derivative, hopefully only one more. Let's see, what's the fourth derivative? That should be the derivative of this expression. Maybe I'll distribute this minus 4 ahead of time. That would be minus 8 dy dx minus 4 x d squared y dx squared. So let's see, what's the derivative of this? This should be minus 8 second derivative minus 4, and then product rule here, similar to what we were looking at before. How about first derivative of the second? Plus, how about second derivative of the first? So let's see, what do we know? We know that at x equals 0, that this term is minus 3. We know that the third derivative is 0, x is 0, and the second derivative is minus 3. So what are all these things? I think this is going to be non-zero. We're going to get, let's see, negative 8 times negative 3 is 24. Minus 4 times 0 is 0. Minus 4 times minus 3 is 12. So fantastic, another non-zero term. So let's put all this together. Our Maclaurin polynomial then is the constant term, which is 1, plus first derivative over 1 factorial times x, plus second derivative over 2 factorial times x squared, plus third derivative over 3 factorial times x cubed, plus fourth derivative over 4 factorial times x to the fourth, which works out to be 1 minus 3 halves of x squared plus 36 over 4 factorial. That's 36. 4 factorial is 4 times 3 times 2 times 1. That's 24. 36 over 24 is also 3 halves. X to the fourth. Part B asked us to find the exact solution to this. And this is a first order differential equation that is separable. So this is very possible. This is, I know it's separable because I can factor an x out. Of this side, and now I can separate this. I can get the dx on the right, the 1 minus 4y on the left, and we can do some integration here. So I think this is like 1 over 1 minus 4y dy, and this is x dx. So if I integrate both sides, my handwriting is sloppy right at the moment. Let's see, the antiderivative of 1 minus 4y is, it should be 1/4 or minus 1/4 of the natural log of this from a u substitution. This is minus 1/4 the natural log of 1 minus 4y. And this should be equal to x squared over 2 plus c. So let's see, what should I do to this? I think I multiply both sides by negative 4. And I get natural log of 1 minus 4y. And this is equal to, multiply both sides by negative 4, I get minus 2x squared, plus a constant times another constant, just a bigger constant. I won't bother multiplying it out, just lump it in with the constant. Okay, our trick for undoing natural log, let's make all of this as an exponent of e. So 1 minus 4y is equal to e to the minus 2x squared plus e. Or better yet, our trick of using exponent properties, e to the c is a constant times e to the minus 2x squared. So the only thing left is to do a little bit of algebra rearranging here. If 1 minus 4y is equal to some constant times e to the minus 2x squared, then I'm going to subtract 1 from both sides and divide by negative 4. So y is equal to some constant times e to the minus 2x squared minus 1 all over negative 4. we know from the initial condition, that when x is 0, y is 1. So we can use that to find, lastly, we'll use that to find this constant, and we'll be done. So when x is 0, so y is 1. So 1 is equal to this constant times e to the 0, which is 1, minus 1 over 4. Multiply both sides by 4. And it's supposed to be minus 4 here. So this is minus 4. This makes more sense. Add 1. And a is equal to minus 3. So put this together in our closed form for this differential equation. A is equal to minus 3 e to the minus 2 x squared minus 1 over minus 4. Or maybe we could multiply everything by minus 1. Finally, we'll do one more similar problem, but with quite a different result, I think, in the end. Here's a differential equation. dy dx equals 2x plus y over x. This time we know that the value of the derivative is 1 when x is 1. And we're going to find the first 3 non-zero terms of this Taylor polynomial centered around x equals 1. So just like before, we need to know what is the value, what is the initial condition, what is the output, or what is y when x is 1. It's not stated, but we have this relation we can find. Since we know when x is 1, we know that dy dx is 1, and therefore let's find x. 2 times 1 plus y over 1. 1 equals 2 plus y, or y equals negative 1. So our initial condition is negative 1. So we have one of our 3 non-zero terms. Dy dx is 1, so there's our second, there's our f prime, or there's our second term. That's good. Dy dx is 1, which means we have our 2 non-zero terms. We just need a third. So let's find the second derivative. Which is just the derivative of 2x plus y over x, which derivative of 2x is 2. Derivative of y over x, quotient rule, low d high, minus high d low, over low squared. We know what x, we know at the center when x is 1, we know what y is, and we know what dy dx is. So when x is 1, we know that, well, obviously x is 1. We know that dy dx is also 1. We know that y is a negative 1, and we know that x is 1. So this works out to be 2 plus 1 minus negative 1 over 1, which is 4. That's good. Well, therefore, we know we can calculate our first 3 non-zero terms. X is, we know that the Taylor approximation for the first 3 terms should be the first term, which is negative 1, plus the first derivative, which is 1, over 1 factorial times x minus the center. And since we're centering at 1, it'll be x minus 1, plus the second derivative, which is 4 over 2 factorial times x minus the center squared. And if we simplify this a little bit, this isn't so bad. We can actually do some nice combining of like terms here. 4 over 2 is 2. We know what x squared minus 1 is, so maybe we'll carry this out a little bit farther than normally we would. 1, negative 1, plus x minus 1 plus 2 times, let's see, x minus 1 squared is x squared minus 2x plus 1. Well, let's see, this is x minus 2 plus 2x squared minus 4x plus 2. And let's see, minus 2 plus 2x minus 4x is minus 3x. So I think this actually simplifies to minus 2x squared minus 3x. Again, you didn't necessarily have to do it this way. You could have left it as minus 1 plus x minus 1 plus 2 times x minus 1 squared. That is perfectly acceptable. But I think we're going to see that this is going to be nice, and it's going to lead to a pleasant result when we do, and kind of cool when we do part B. To that end, let's solve this thing exactly. This to me is not separable. I don't know a good way to separate this out. However, it is dy dx. It does have y times a function of x and a individual function of x. So I think we could rewrite this and use the integrating factor method from the previous lesson. So let's do that and get some practice with that. So let's rearrange this a little bit. Let's get it in that form that we'd like, dy dx. I'm going to subtract the term with the y, minus y over x, and that was equal to 2x. This is in our form dy dx minus a function of x times y equals a function of x. This tells me that what we called p before, this is the polynomials multiplied to y. That's minus 1/2, or not 1/2, but 1 over x, minus 1 over x. Therefore, the integrating factor, if you recall, is e to the antiderivative of p to the x, or not p to the x, of px. So that means we need to calculate what the antiderivative of p of x is, and then we're going to make that the exponent of e. Therefore, that means we need to find the antiderivative of minus 1 over x, which is minus the natural log of x. Or minus the natural log of x, that's like minus 1 times the natural log of x, which is the natural log of 1 over x. Thus, the integrating factor is e to the natural log of 1 over x. So, that means we do the following. We should multiply this differential equation through by the integrating factor, through by 1 over x, resulting in 1 over x times dy dx minus 1 over x times y over x is equal to 2x times 1 over x. Recall the reason we're doing this is because we can recognize that this is exactly the same as the derivative with respect to x of the integrating factor times y. And 2x times 1 over x is 2. So if I want to solve for y, I can integrate to undo this differential operator. So I'm left with 1 over x times y is equal to 2x plus c, or y is equal to 2x squared plus c times x. We know from the initial conditions from part A that when x is at its center at 1, y is negative 1. So we know this initial condition, we know that when y is negative 1, x is 1. Which tells us that negative 1 equals 2 plus c, or c equals negative 3. So substitute that in, and we get the exact solution of y equals 2x squared minus 3x. This is note that this is kind of interesting in that the solution to this differential equation that we got, this exact solution, ends up actually being the same as the first order, or the Taylor approximation of this series. So in effect, we could have solved this using the approximation method according to Taylor, and we would have got the exact solution as it was. So we didn't actually have to go. So this integrating factor method of finding the exact solution was actually more work than we actually was necessary, because the approximation not only was good, it provided the exact answer.